Be back in Boulder and see so many friends and colleagues. And is this not working now? What did I do? Is it okay? All right. Okay. And see so many friends and colleagues whenever I come here, and really appreciate the opportunities to interact in the summer and other times of year when Bill and I come here. I put up this figure because I didn't have time to put it into my PowerPoint. Typical of Boulder, I ran into Shin Lin at Whole Foods at lunchtime today, and I told him that I was going to be showing this now famous figure from Sampex that I'll put in context in a moment. That he has been extending over time until finally it collectively shows 2 solar cycles, basically, of 2 to 6 MeV electron data from the low-altitude polar orbiting Sampex satellite. And I might as well tell you about it now, and then I can skip through the part that's in my PowerPoint. So this is a kind of format that I'm going to use also for showing more recent data from Van Allen probes, where you have radial distance along the y-axis measured in units of Earth radii, and you have time going across the x-axis here. So 2 solar cycles worth of data, 2 to 6 MeV electron fluxes. These are 30-day averages. And in the top panel, you see the sunspot number, average sunspot number in black, and weekly averages of solar wind speed are shown in red. And so when I come to a slightly earlier version of this slide, I'll have things labeled, but you'll see that this time period around here is the declining phase from solar maximum, the 90-91 solar maximum. And this is the rise to the next solar maximum, and then you have the declining phase again. And so one of the things that will become apparent is that the absolute maximum flux in terms of 30-day averages is not at solar maximum, but during the declining phase when you have recurring high-speed streams, as are indicated on the top. So you'll have another chance to see this again as I go now to my... No, that is solar minimum. Whoa, that is not a data gap. Yeah, so I'll say a little bit more about that. So here's my actual lead-off PowerPoint then, with appreciation to colleagues, some of whom are here, who've contributed to this talk, where I'm going to focus on the radiation belts. This is kind of a canonical view of them, which turns out to be completely incorrect because it gives you the sense that they're this very stable structure. I'm going to be focusing on the outer zone, which is made up of electrons extending up into relativistic energies, rather than the inner belt, which is primarily protons. And I'll say a little bit about what causes the slot region in between those 2 zones. So I'm going to talk about geomagnetic storms affecting the radiation belts and acceleration processes. It turns out that the Earth is an extremely efficient accelerator of particles up to MeV energies. I'll talk about loss processes, and then I want to highlight recent observations by the Van Allen probe satellites, which were launched end of August last year, and then say a little bit about the Barrel Antarctic Balloon project that's being run by Robin Millen at Dartmouth, which is measuring precipitation of these radiation belt particles into the atmosphere, which is a significant loss process. So here we have an earlier version of Shin Lin's figure again, first published in 2006 and then updated in 2011 and updated again today at lunchtime. So I should say that Sampex finally entered the atmosphere in November, I think it was, and so November 13, yeah. So it just overlapped for a couple of months with the Van Allen probes. And so in this earlier version, then I have marked the time period from the declining phase of the 90-91 solar maximum, where you see high-speed streams indicated at the top, These are CIR-driven storms that are responsible for this significant flux enhancement that you see in 30-day averages. And then over here, when we're rising up towards the next solar maximum, these are primarily CME-driven storms, and although you can get faster and higher flux rises for shorter periods of time from the CME-driven storms, when you take a 30-day average, you see that the CIR-driven storms give you higher fluxes in that average sense. And so then here is, again, the declining phase from the most recent solar maximum, and so you see again the very strong enhancement in flux associated with high-speed stream-driven storms. Then we're tailing off here towards this, what Stan asked, is that a data dropout? And that's the, I'll show you on the next slide, a blow-up of that time period. That's the very recent, very strong, strongly suppressed activity during solar minimum. And so at the top, you see solar wind velocity plotted again. And now the whole time period from 2003 to end of 2009 is shown here. And then the 2007 through 2009 interval is blown up. And so you can see that the radiation belt outer zone electrons here, here's the inner zone, the outer zone is just vanishing away. And so I'll go back and put up the PDF that I started with so you can see the big picture again. But this was a very deep solar minimum in which the outer zone virtually went away, and we think that a significant piece of that is the absence of strong solar wind driving that you see evident in the solar wind velocity profile. So so here again is that figure. I did manage to paste in post lunchtime the figure that shows this what Stan called a dropout here, which is not a data dropout, but just the absence of outer zone electrons due to absence of solar wind driving at solar minimum. Okay, so now the good news for those of us involved in Van Allen probes is that we are coming back up again. So there is a solar maximum, even though it's a more modest one, and you can see that in the sunspot number here. So if you compare our current solar maximum to the last solar maximum, you see that we're down quite a bit in terms of sunspot number, and in particular, the solar wind velocity is suppressed relative to what it was at the other solar maximum. And so we haven't quite gotten the kind of strong driving that we had the last two times around. But let's see, before I go on and talk about the recent recurrence of solar maximum, I'll just mention, because it was a joint activity here when we visited and I collaborated with Mike Wiltberger on a project that was sponsored by CISM, the Center for Integrated Space Weather Modeling. We studied collectively, the whole CISM multi-team studied the WE interval, which I know was an interval that was studied by a number of people here. And that was a period in March to April 2008 where there were two high-speed streams that you see here. The solar wind velocity is plotted negative because we're very Earth-centric in the magnetosphere. And so this is a high-speed stream, this is a high-speed stream, and there you see the compression of the density ahead of the high-speed stream. And Mike ran this entire time interval using the CMET code, which couples LFM, that I'll talk about a little more, to TIG-CM. And we used the output from his simulations. In particular, he reran for the two high-speed stream intervals at higher time resolution with the LFM code. And we pushed test particles, which is kind of what my group does, and I'll show you results of those kinds of simulations. And I'll just put up this without saying too much more about it. The result of the test particle simulations riding along on the MHD fields was to reproduce the flux enhancement that was seen at 600 keV by GOES that was associated with the first high-speed stream. So I bring this up as recent past work that we've done collectively using codes here. All right, so let's come back now to this rise out of the long, deep solar minimum. So move on from the 2008 interval on up to this recovery that we're now seeing. And we're now seeing CME-driven storms again. So that was the good news. We aren't in the middle of a Maunder minimum. So otherwise it would have been really bad news for Van Allen probes, I think. So Van Allen probes were launched August 30th of last year, and they're twin spacecraft in an orbit which goes from 600 kilometers out to 5.8 RE in a 10-degree inclination. So they're designed to slice in and out of the radiation belts, and they're identically instrumented and have just spectacular, as I'll show you, particle instrumentation for giving very high time resolution energy and pitch angle measurements, as well as electric field and magnetic field measurements. And then this I'll come back to, shows you something about the barrel balloon campaign, which is being run out of Dartmouth by Robin Millen. And the idea there is that she and her colleagues are launching balloons every day or two from two different stations in Antarctica in order to set up an array, a longitudinal array of balloons, and I'll try to get to some of those results at the end. So that because it's essentially impossible to measure particles in the loss cone out at the altitude of the Van Allen probe satellites. So they don't resolve the loss cone on the Van Allen probes. And so to get a handle on how much of the change is associated with precipitation, it would be great if we continuously had SAMPEX down at low altitude, but SAMPEX lasted longer than anybody expected, mainly because of the long solar minimum, so it didn't come into the atmosphere as soon as people expected. And Shinlin Lee, you should invite to give a talk, or Lauren. You did? Okay, so you've heard his story, or Lauren Bloom, who has been project manager for that. So that satellite, for the time period that it lived, gave us a handle on the low altitude precipitation when you have a low altitude satellite. But did it start up again? Good. So the rumor at GEM was that it was on again, so this is great. Excellent. Okay, and there's going to be another one or two, I think, launched in December. Harlan Spence at UNH is, again, developing CubeSats. Meanwhile, this is a different technique, and I'll describe it a little bit later, but Robin uses detectors on her balloons that measure the Bremsstrahlung X-rays produced by electrons precipitating into the atmosphere. And the thing that's nice about the balloons is that while satellites are just going over very quickly and cutting through L values very quickly at low altitude, the balloons they're in a different kind of geostationary orbit. So they are staying at approximately constant location during the course of significant geomagnetic activity, drifting very slowly in longitude. So that's one thing. And then the other thing is that then you have this longitudinal array, which gives you an idea of the spatial extent of the precipitation that's hard to get even from just two spacecraft. So I'll come back and show you a little bit more about the nice results coming back from Robin and her students and colleagues who launched 20 balloons from Antarctica from these two stations, Sinai, the South African, and Halley Bay, the British station, that then drifted counterclockwise, setting up an array. Okay, so back to the Van Allen probe results. This is a synoptic slide from the relativistic electron-proton telescope built at LASP over at University of Colorado. And this is the highest energy of the ECT instrument suite, which I always forget what the acronyms stand for, but the main thing is that this goes from the energies that are indicated here down around 2 MeV on up to about 8.8 MeV. And this is 9 months or so of data. And I'm going to zoom in on this little postage stamp piece right here, sort of the first 40 days of data in September and early October, and talk about that in a moment. But one of the things you'll see is that there was a lot of activity around the equinox here, and there's more activity around the March equinox. This is a statistically significant, repeated year after year phenomenon that the radiation belts are more intense around the equinoxes than they are around the solstices. And I'm sure that most people in the audience have heard Bob McFerrin talk about this. Yes, I hope, because I'm not going to go through and talk about the orientation of the angle of the Earth's magnetic field relative to the interplanetary magnetic field and why the equinoxes are favored. And even that is, Bob has now concluded, is not perhaps even as significant as the heliographic longitude of the Earth relative to the sun's equatorial plane, which affects the solar wind velocity that increases as you move away from the solar equatorial plane. And so there's higher velocity solar wind around the equinoxes as well. And I'll argue as we go along that higher velocity, as we've seen already in Shin-Lin's slides, affect the radiation belts. So I'm going to zoom in on this time here, but keep in mind this major storm which occurred in October 7 to 10, that affected the radiation belt electrons all the way up to 8.8 MeV energies in such a way that once you get electrons up to energies that high, it's hard to get rid of them. And so they are staying around for months and months, slowly decaying away, radially diffusing inward in time until sort of the next round of activity in March. Okay, so zooming in on that postage stamp. So it's this time slot right here, sort of the first 40 days of turn on of the REPT instrument, which happened right after launch. So at the very beginning of September, REPT was the first instrument that was turned on in the hope of getting some overlap with SAMPEX, because it was known that SAMPEX was going to go into the atmosphere pretty soon. And so you see, this is again this same type of plot where you've got radial distance measured in Earth radii and time going this way. And at the very beginning, there is a normal inner zone, outer zone structure. So this bright red spot right here is the outer zone, and this is the inner zone down here. And then if you look down at the solar wind data, there's a CME-driven shock, a high-speed solar wind here that's associated with the CME a couple of days earlier back at the sun. And then this shows the interplanetary magnetic field direction, or at least the magnitude and the BZ component. The BZ component turns out to be very important for coupling efficiency to the magnetosphere, because when BZ is south and the Earth's magnetic field is coming out of the South Pole and is north, then you get a very efficient reconnection on the day side, and you enhance the coupling between the solar wind and the magnetosphere. I'll write down an equation in a minute that just describes that coupling. And then down here at the bottom, this is a geomagnetic index, but it's my favorite index because it's measured in real units. It's measured in nanotesla. And it is the disturbance of the horizontal component of the Earth's magnetic field at the equator due to buildup of the ring current. So I'll show you a figure in a bit that shows convection from the tail of plasma in the tail region where plasma is stored, the so-called plasma sheet. And you get enhanced convection when you have enhanced solar wind driving. And then when ions and electrons come into the inner magnetosphere, the ions drift one way and the electrons drift the other way due to the gradient curvature drift. And that gives you a current in the direction that my thumb keeps pointing. That gives you a current in the direction of my fingers in a magnetic field that is opposite the direction of the Earth's magnetic field. And so you get a suppression in the horizontal component of the Earth's magnetic field when you have enhanced ring current and enhanced convection. So that's what this DST parameter is measuring. And you'll see that each one of these major depressions in the Earth's magnetic field due to buildup of the ring current is correlated in this case with a CME shock feature in the solar wind that you can pick out either in the magnetic field or in the velocity. So, so going back to this period right here, you have a CME-driven storm, And so what I'll argue from simulations that we've done is that the magnetopause moves earthward due to the CME shock compression of the dayside magnetopause. And when that happens, electrons out at larger radial distances get lost to the magnetopause. And so that's the main mechanism that's responsible then for this bite out in the outer zone that you see here. Then this white line that's being plotted is the so-called plasma pause. So it's the boundary of the plasmasphere, which is I could think of the plasmasphere as the upward extension of the ionosphere that's co-rotating with the Earth. And that plasma pause gets moved earthward when you have enhanced convection for reasons I won't go into the details on. And so this is from a model that was developed by my former PhD student, Jerry Goldstein. And he developed this model based on data from the IMAGE spacecraft. Over time, he developed a model that followed the convection of cold co-rotating plasma as a function of the convection electric field and solar wind driving. And at the time of this particular dropout, the wave instrument had not been turned on yet on Van Allen probes. And so we didn't have any handle yet on what the plasma density was from the spacecraft in order to say where the plasma pause was. But by about this time, mid-September or so, the University of Iowa instrument was turned on, and it measures high-frequency waves up to the upper hybrid frequency, and you can use that to cross-calibrate with Jerry's model of the plasma pause location. And so that comparison was very good. And so, but at the time that this paper was written by Dan Baker, published in the first quarter of the year in Science, we didn't have all of the Iowa wave data available, just enough to check Jerry's model at a few points. And so this shows that during this time period, after the storm, after the strong solar wind driving has stopped and the solar wind velocity has gone down again, you see that the plasma pause recovers and it moves outward in radial location. And now you have the persistence of this feature, which is it's basically the leftovers of the outer zone, is how I think of it. So you had the strong erosion of the outer zone due to magnetopause inward motion due to the shock. And then you have a recovery, the magnetopause is moving outward again, and the outer zone is reforming. But you have this residual feature here, which is left over from the pre-existing outer zone, which Dan referred to as a storage ring in the Science paper. And so what happens is that these electrons are inside the plasmasphere. And inside the plasmasphere, there's only one kind of wave present, which is efficient at causing electrons to scatter in pitch angle. And it's a form of Whistler mode called Hiss. And so these waves have frequencies comparable to the electron gyro frequency, and they cause the electrons to lose track of following the magnetic field line. And they scatter in pitch angle and wind up in the atmosphere as a result of interacting with these waves. But the time scale for that to happen at these high energies, these particles are like 4.5 MeV. The lifetime is long, and so you can see that this population persisted for a month inside the plasmasphere once it survived the erosion that was caused by the inward motion of the magnetopause. Then you have another even stronger storm come along at the end of the month, and this one pushed the magnetopause in further, and we know that from the MHD simulations that we did for each of these events. And so when that happens, it basically wipes out what's left of the storage ring. It begins to recover, and then you have yet another strong CME-driven storm, and that really completely wipes out the outer zone. And then bang, something pretty exciting happens, because you have a very rapid increase in the relativistic electron flux on a time scale of hours that completely replenishes and gets you back to ahead of where you were at the beginning of the month before any of these CME-driven storms occurred. So that's a pretty exciting story that the Van Allen probes team is working on, explaining that rapid recovery in flux after you have essentially flushed the outer zone. Okay, Yeah, that is the 3-belt. Okay, yeah.
The thing that's confusing when I look at that, so the 3-belt ends, but I still see 3 belts after the white line up there. I'm just wondering what.
Well, so here at the beginning you see is the normal 2 belts, inner zone, outer zone. But then because of this so-called storage ring, which is the residual of the outer zone prior to this early September storm, that is persisting, and it's just slowly decaying. In fact, Richard Thorne has a paper describing the very slow decay of the storage ring due to the hiss. And then you have the normal reforming of the outer zone that is occurring, and that's the 3-belt structure right there, 1, 2, 3. And I heard a NASA administrator, John Grunsfeld, stand up and refer to the 3-belt structure and refer to this as the new belt. And that's not, that's the usual old belt. And the thing that's new in this particular observation was this storage ring. But now people are going back and looking at earlier data, CRRES data, and seeing the multi-belt structure pretty clearly in other observations. Yeah, Janet? Oh, yeah, you want me to go back? Yeah. So you look at that, and on this scale, at this energy is 1, 2, 3. Yeah. But here, I don't know. I'm not seeing this. So you're saying that these particles are always there. It's just that very often they're merged together into one. Yeah. Yeah, it's true, but it depends on the energies that you're talking about. But yeah, you can look over. So your point is just that. Well, but it is left over from the previous. I think it's left over from how far in at the beginning. So this is the September time, and so here it's really clear: 1, 2, 3, right? And so where do you want to talk about there being 3 again? Here I see 2.
It also depends on energy.
Oh, yeah.
High energy don't stay during that period.
Yeah, there's no source for getting the higher energy electrons replenished after this October storm, right? So something special happened in the October 7 to 9 time frame, right? Yeah, but yeah, no, okay. So maybe I can see it better on my laptop than I can here. But here maybe there's 3, right? I can see it better on my laptop. But at any rate, I think that people are going back. I've seen now papers submitted on using CRRES data where this kind of residual belt and then that survives because it's inside the plasma sphere after the recovery, that hangs in there because the loss rate is so slow due to hiss, and then you have a formation of the usual outer zone at higher L, and again I can see it a lot better on my laptop, but you have then particles diffusing in at higher L that are filling things in. I guess this is the one I'm looking at, but it's easier for me to see on here than it is on that kind of scale. But this is just the normal outer zone formation relative to this, which is left over from the pre-existing outer zone.
I don't see it coming back when you get this new second outer belt again.
No, I don't. There's a 3-belt structure there because there's still a little residual. Yeah. It's not a formation phenomenon. It's a persistence phenomenon. And I hope that came across in the paper. Tried to go through and X out any place that talked about new belt, because it's basically the old electrons hanging around. Yeah. Yeah, El Sobrante, right? Yeah, the leftover. Okay, so I'm going to talk about mechanisms for flux increase and say something about radial transport mechanisms. So I'll say a little bit about prompt acceleration by CME shocks, which are an old-time favorite of mine and Shinlin's, and then some new results on the enhancement associated with enhanced convection, some nice recent simulations by Brian CRRES for that October time periods, October 7 to 10 time period. I say something about ultra-low frequency waves and their effects. These are waves that have frequencies comparable to the electron drift frequency, and I described this last week at the CISM summer school as being like pumping a child on a swing. If you give an electron a kick at a frequency that's comparable to its drift frequency, then it's possible to pump up its energy. And then these local acceleration are associated with waves that have frequencies comparable to the electron gyro frequency. And so in that case, an electron can see a constant electric field in its rotating frame of reference, and that will accelerate it. And then the competition between acceleration and losses, and two distinct types of losses. One, radial losses to the magnetopause, and the other losses to the atmosphere. So that's way more than I have time to talk about. So I just flashed this as the first poster child for prompt acceleration by CME shock. Shin Lin worked on this particular storm back in the mid-90s and developed a simple model that showed that the electrons were accelerated and transported radially inward and accelerated up to these very high energies that you see here. It's like before and after, and that occurred on a drift time scale of an electron. And at these energies, that's like a couple minutes. And so that was the first event that really got our attention, that you could really drastically change. This is the entire 14-month lifetime of CRRES, that you could drastically change the outer zone on the time scale of a couple of minutes. So we've seen that kind of effect since then. The Halloween storm in 2003 got a lot of attention. And what you see, this is SAMPEX data again, depends on the energies that you're looking at. And this is the 2 to 6 MeV channel that we've been looking at, and this is greater than 10 MeV. And if you looked at these two, you would say, oh, wow, it took longer for something to happen at 10 MeV than it did for it to happen back around Halloween at 2 to 6. This is the actual Halloween storm right here. But you would be wrong because SAMPEX is down at low altitude, and so I'll show you that the acceleration that occurs associated with the shock increases the particle's perpendicular energy, not its parallel, and it does so dramatically. And so V perp over V parallel affects the pitch angle of the particle. So that's relative to 90 degrees. And so particles which have a sudden big increase in their V perp will wind up mirroring close to the equator. And at these high energies, there aren't waves around that are very effective at scattering them in pitch angle. And so it takes a couple of months for them to show up to scatter into the loss cone and be seen down at the orbit of SAMPEX. And that was put forward in the observation paper by Mark Looper. So what we did was simulate this event with the LFM code, and I'm imagining that everybody here has heard about that. So we used the L1 measured input, which we didn't have for the March 91 storm. And we use that as the input at the upper boundary to LFM and calculate the MHD time series in three-dimensional space. And then Brian CRRES used that to push guiding center electrons. So electrons where you're just following the center of the gyro motion. And so this shows, looking down on the equatorial plane, two snapshots of the azimuthal electric field, first of all, and then I'll say something about the electron trajectory. So when the shock hits the magnetosphere, you compress BZ coming up out of the equatorial plane in the direction of my finger, and Faraday's law gives you an azimuthal electric field. And so that's what's plotted, and that azimuthal electric field is pointing clockwise. And electrons are drifting counterclockwise, so they're accelerated by that electric field. So V dot E is in the right direction to be accelerating the electrons. And so the upshot of that is there are a couple of ways to look at it, but the electrons are conserving their perpendicular energy over magnetic field strength. That's the magnetic moment of the particle. And so as their perpendicular energy increases due to that electric field, that causes the electrons to have to move radially inward to a region where B is stronger. Since W perp's increasing, B's got to increase, and so they move inward. And so this is a snapshot at this time here, and just it looks like a matter of seconds later here. And you see that this electron that started out at 5 MeV, so this was pretty energetic to begin with, at 6 RE is transported inward to 2.5 RE, where now its perpendicular energy is 15 MeV. And so that's how you get that sudden appearance of the 13 MeV population that you saw in the CRRES data. So this is a rapid acceleration of very energetic electrons. Now, here's the catch. The electrons have to be drifting approximately in sync with the azimuthal electric field impulse as it's propagating through the magnetosphere. And it propagates at about the Alfvén speed. So that's 1 to 2,000 kilometers a second. And if you do the calculation, it means that the electrons already have to be up in the MeV energy range, the order of an MeV or greater, in order to be constantly seeing, so you see here and here, the electron is still seeing the very strong azimuthal electric field as it drifts around. So it's a kind of surfing mechanism. If it's a low energy electron, this pulse washes over it, and it doesn't spend very much time in the azimuthal electric field and doesn't get much acceleration from it. So this just shows you the trajectory of this electron and its location at these two different times, and this is the energy increase that the electron gets as a result of the radial transport. So Brian made this kind of map where you're looking down on the equatorial plane now at 100,000, 200,000 electrons in the simulation. And initially, he had no electrons above 10 MeV, so he started with a 1 to 7 MeV population. And what he's plotting is the greater than 10 MeV electrons as they cross the equatorial plane. So they have bounce motion as well as drift motion. And so you can imagine that there's a blue plot over here off to the left before the shock arrives, and there were no greater than 10 MeV electrons crossing the equator. The shock arrives, and now you have some that are accelerated and drifting around, and more are accelerated and drifting around, and more. And pretty soon you have a pretty substantial population of greater than 10 MeV electrons as a result of this CME shock interaction. This is just a plot of the pitch angle distribution that results to explain the SAMPEX observations. Brian started with a strictly flat in pitch angle distribution, but because of the increase in V perp over relative to V parallel, they wind up being strongly peaked at 90 degrees. Okay, now I want to go on to more recent storms, and so this is this famous October 7 to 9 storm where you saw the dramatic increase in flux seen by REPT. And I'm going to show you results from, again, a simulation by Brian Kress that's going to focus on this time period. Now, what was one thing that's really significant about this storm is this very long period over a half a day where you have very strongly southward IMF. And that was driving substorm after substorm, if you look at AE for this time interval. And so you're continuously injecting electrons from the tail that are the source population for building up the MeV electrons. And so Brian focused on the recovery period here, where IMFBZ is going from very strongly southward to recovering back towards northward. And what happens during that time period is any enhancement you have in flux will be amplified by the fact that the Earth's magnetic field then is relaxing back to what it was before you had the very strong driving, very strong ring current due to this many, many hours of southward BZ. So this is Brian's simulation, and now, unlike the previous one I showed you where he was looking at already trapped electrons, here he's injecting electrons continuously from the night side, from the tail, from the plasma sheet over here. And they're drifting in, and then they begin to drift around to the dawn side because of the gradient curvature drift. And then as they do so, they're becoming energized because they're moving into a region of stronger magnetic field. And now you get a relaxation of a boundary between electrons, plasma sheet electrons that are just drifting to the magnetopause, that's the blue, and ones that have become trapped and energized are seen here in green all the way on up to red. So he's showing here that during this 3-hour time period, you're getting substantial injection and trapping and energization of plasma sheet electrons up to MeV energies. Now, is that enough to explain that bright spot in the REPT data? No. But what it does is it gives you a source population at MeV energies, which is what is needed for the mechanism of local acceleration by interaction with whistlers. So it turns out that it's one of those cases where the rich get richer, so you need energetic electrons to begin with to interact effectively with the whistlers to get efficiently accelerated up to higher energies in larger numbers. And so this is showing how the magnetospheric convection is giving you an enhanced source population during this time. Okay, so I won't spend much time on this. This is another type of event, another CME shock that just is meant to show that you get oscillations in the azimuthal electric field and oscillations in the magnetic field subsequent to the arrival of a shock. This was a measurement from for cluster spacecraft, and I don't want to spend a lot of time on this. You know what I'm going to go on to? I'm going to go on to this figure right here because of time. So this is another Halloween storm, this one 2012. And this is data, again, from the Van Allen probe satellite, and it's a very nice figure produced by Seth Claude-Pierre, who was a PhD student at LASP at CU, and he's now out at Aerospace in Los Angeles. And Aerospace is in charge of the medium instrument energetic particle instrument, MAG-ICE, which is just down a step from REPT, and it overlaps with the REPT instrument. And so what you have here is, again, an arrival of a CME shock right here, and that was preceded by a substorm over here. And what's plotted are different energies of electrons as measured by the MAG-ICE instrument, and this is the color code over here that shows that they are measuring now from the 22 keV range all the way up to 3.8 MeV, so you can see they overlap with REPT. And that's really been critical for cross-calibrating the two instruments, to have two completely different types of instruments that have overlap. And so you see that you start to see an enhancement of the flux of the low energy electrons. So whenever the flux is higher, you're talking about the lower energies, just associated with the substorm injection of Plasmasheet electrons from the night side. And then the CME shock arrives and compresses the magnetopause, and you get these ringing oscillations at ULF wave frequencies that were also present in the cluster data I didn't elaborate on. And so there's two different things going on here. At the very low energies, all three of these, and also down at some somewhat higher energy channels, are oscillating at the same frequency. So these electrons are just responding to the ULF waves. Then if you go to higher energy channels down here, this oscillation frequency here is so-called drift echoes. And so it's a longer period, and you can calculate the drift time of electrons around the Earth at that L value, and it corresponds exactly to the frequency that you're seeing here. And this is a blow-up now of three of the higher energy channels that are seeing the drift echoes. And the vertical axis here is actually pitch angle, but it hasn't been converted to pitch angle on this particular slide. And so I just want to point out that as you move down in energy, up in energy, so this is the higher energy channel here, this is the lower energy, you see that the drift echoes are occurring at higher frequency because the particles are more energetic, and so they're drifting around faster. And then this kind of slant that you're seeing as a function of pitch angle can be converted into, you can understand it because the drift frequency is pitch angle dependent. So there's just a gold mine of fine scale information that's available in RBS, in the Van Allen probe data, that is much more again, it gives us a lot more information than we had from other spacecraft, because we've never had this kind of energy resolution before. We've never had this kind of pitch angle resolution before in order to sort out what's drift echoes, what's ULF waves. Yeah. Those are so-called sectors, and if you now go to the ECT website, you can see that you know that there are versions of this that have been, and certainly for publication, I think you know Seth has now submitted this to GRL, and he's converted it to pitch angle. Yeah, because these are again, it's a spinning spacecraft, and that's how they're doing the pitch angle information, and so those correspond to different sectors of the spin period.
Well, this number like 268, those are energy flux, the AeV.
No, this on the y-axis right here, that is a sector. That can be converted to pitch angle, whereas these are corresponding to different energies that I don't think are labeled on this particular plot, but you can see that they are labeled down here. Yeah. So what does that have to do then with accelerating electrons? Well, the ULF oscillations have, let me go to this one right here, have a history of being correlated with a rise in relativistic electron flux at geosynchronous. So here is a different class of storms rather than CME-driven storms. This was back during the declining phase from solar maximum during the first solar cycle of SAMPEX. But this is comparing the flux at geosynchronous with the ground magnetometer measurements of ULF waves. And so you see that the ULF wave power increases with about a couple of day lead time on the rise in the relativistic electron fluxes at geo. And so what is causing this rise in ULF wave power in this case, not a CME shock, but a high-speed stream? And so how do you go about exciting ULF waves in the magnetosphere in this case? There are a couple of mechanisms that have been published in the literature. Pressure oscillations in the solar wind are seen to map into magnetic field oscillations at geosynchronous with the same frequencies. So that's kind of a direct deriving from solar wind pressure oscillations of ULF waves in the magnetosphere. And then the other way that has been investigated by Seth, and I'll show you a figure from his thesis, is the excitation of Kelvin-Helmholtz instability along the flanks of the magnetosphere. As you increase the velocity of the solar wind, and that's what Seth's figure shows, you increase the power in oscillations that have a frequency comparable to the electron drift frequency. And so that's what's being shown over here on the left. And so it's this idea that if you are pumping the electrons with an electric field oscillation whose frequency is comparable to their drift frequency, then it's possible to energize them. And so that's the connection. And then if you increase the solar wind velocity, whether it's due to a high-speed stream or it's due to a CME shock, both of those are going to amplify ULF wave power in the magnetosphere. Okay, so I don't have time to say anything about local acceleration other than that it's important. And you need to invite Richard Thorne to come here, or someone from his shop, to talk to you about the fact that when you transport plasmasheet electrons earthward and plasmasheet ions due to enhanced convection, this is looking down on the equatorial plane, the electrons drifting around to the dawn side excite Whistler chorus, and the ions that's around the electron gyro frequency. Ions excite ion cyclotron waves around the ion gyro frequency, and both of them can interact with the electrons. Only the chorus produces acceleration. They both produce loss to the atmosphere. We have some cool simulations by Dartmouth PhD student Shor Wu of this that I don't have time to talk about, but next time I'm here, I want to invite Shor to come and talk to you about her hybrid simulations in dipole geometry of the chorus. Okay, so back to Van Allen probes. I do want to talk about the evidence that local acceleration was important for this October 7 to 10 storm. So this is a paper that just came out in Science last week by Jeff Reeves and colleagues using data from the ECT instrument. So this combines REPT and MAGICE. And so this is a plot that shows a time sequence that starts down here with the lower fluxes that you'll remember we had before the very strong flux enhancement. And then it marches up in time on, I think, October 8th. And that you get to this point right here where this is a so-called phase space density profile. So it's been converted from flux into phase space density, which is the F in Vlasov, the Vlasov equation, averaged over gyro phase, bounce phase, and longitude phase, drift phase. And so you see this very pronounced peak in phase space density. And you can't really explain that by any kind of radial transport or radial diffusion like you get from the ULF waves that I haven't talked about in any detail. You can't really explain it with that because any kind of a diffusive process and the radial transport processes tend to smooth out radial gradients. Whereas this is a very conspicuous march from a fairly smooth radial profile to a peak in phase space density. And the thing that really nails it in this article is the two spacecraft measurement nature of the Van Allen probes. And so for this particular profile right here, the green profile, one of the Van Allen probes was coming in an L and the other one was going out. So they're chasing each other on the same orbit, and they separate in orbital phase over time. And one of them was coming in and the other was going out. And if you match up the phase space density point to point as they're approaching the same L value, there's no doubt that there's a peak in phase space density that's occurring at this time when you had this very strong flux enhancement. After that, it tends to get smoothed out, and you would expect that to be the case due to any kind of radial transport mechanism that smooths out a gradient. And you continue to get flux enhancement at later times. But that's the key message from this particular paper, that it requires some kind of local acceleration as opposed to radial transport. Okay, so I have just a couple of few minutes to talk now about the magnetopause losses again. And I mentioned that we've done simulations for each of these three events to examine the importance of magnetopause losses. And so we, in particular, looked at the October 7 to 9 period because you start out over here with a very strong bite out. So you have a very strong loss that's associated with inward motion of the magnetopause. So once again, we use the LFM simulation code to feed in the upstream solar wind parameters from ACE. And this is a plot from that simulation that shows you this black line, which is the location of the magnetopause as a function of time. And you can see that the magnetopause has come in pretty close to geosynchronous here, right at the time that you see the flux drop out on Van Allen probes, formerly known as RBSP. And this is an orbit-by-orbit plot of the flux, and so you see the blue indicates that the flux is dropping out right around the time of the maximum incursion of the magnetopause. And LFM density is what's being plotted in color. Okay, so we did a comparison of how well LFM is doing, and in fact it does much better if you do a run that's coupled to RCM, which includes a better representation of buildup of the ring current. And so the black line is the result for LFM. This is a data point to be ignored basically in the solar wind data. So sometimes you have a bad data point in the solar wind data that you're feeding in. But the main point is that you get a very good agreement between LFM and the SHU model of the magnetopause, which is an empirical model based on accumulation of a lot of data. And then parameterized by solar wind driving conditions. So that gives us a lot of confidence in what we are claiming is the magnetopause location over here in the LFM simulation. The next thing my colleague Jan Peral did was to do an analysis of the ULF wave power for this storm. And this is two different ways of plotting it. This plots the ULF wave power in the 0.1 to 10 millihertz range. Plotted as a function of radial location, and here again is the location of the magnetopause in black. And you see ULF wave power is extending radially inward even into L equals 4 for this event. And this is the arrival of the CME shock right here is the black arrow. And then the second panel shows the ULF wave power now as a function of frequency at a particular location at noon at geo. And you see that there's a lot of power down here in just the 1 to 5 millihertz range, which is just right to be resonant with electrons at MeV energies drifting around at L equals 6, say. Okay, so the next thing Jan did was he pushed particles in the MHD fields for this event, and so this is now doing that and converting to the energy channels of the REPT instrument, and so this is 2.5, 3.5, 4.5 MeV. And again, the magnetopause location is apparent, but you'll notice that even in the simulations, the electron loss is extending inside geosynchronous and well inside the location of the magnetopause. And so you might say, well, how do you explain that in terms of magnetopause losses? The electron gyro radius is minuscule on this kind of a scale. And so the answer to that, we believe, is that the ULF, if you have inward incursion of the magnetopause as strongly as you see it here, and you have enhanced ULF wave power, like you see in these other slides, you're going to have an inversion of the usual radial gradient. And so there's going to be inward motion of the magnetopause, and then it relaxes out. And now you've got a radial gradient in the opposite direction. It's so that you have a drop-off going this way instead of a drop-off towards the Earth. And the ULF waves will then cause radial transport to the magnetopause and enhance the loss well inside the magnetopause boundary. And so that's what you're seeing here. Okay, all right, so losses to the atmosphere, just a quick look at Beryl. I want to say something about the Beryl campaign. This is a very nice CME storm in January of this year, where there was an actual, finally, after weeks of quiet, they went down to Antarctica and they saw like nothing for the whole month of December. They were getting set up, and the first 2 weeks in January, they were launching balloons every day, and the magnetosphere is not doing anything, and the solar wind's not doing anything. And then finally, there was a CME shock on January 17th. And so you see that there was an enhancement in the GOES electrons associated with that. This SIM-H is just another version of DST that's measuring the buildup of the ring current. And so I wanted to put this slide up because I know I've got some GOES fans out in the audience here. So this, this shows a map on the equatorial plane of a location of 2 of the balloons for this January 17th event, and they are just almost exactly on top of the location of the 2 GOES spacecraft. And so you have the balloons down in the ionosphere, and you have the GOES spacecraft out at geosynchronous that are overlapping for about 3 hours here. And I'll show you on the next slide the precipitation that the balloons saw. So what we hope to be able to do is make some connection between flux changes that were seen at GOES and the precipitation that was seen at the balloons. What we really want to do is do that with the Van Allen probes, because they have the very high time and space resolution. Well, they have the very high time resolution, energy resolution, pitch angle resolution. But the problem for January of this year is that the Van Allen probe satellites were over in the dawn sector, and the precipitation was seen in the midnight to dusk sector, and I believe that that was true for all of the Beryl events, but I'm not certain, but certainly it was true for this event. And that will be reversed come, or it won't be reversed, but come next January for the next Beryl campaign, the Van Allen probe orbital plane will be over the dust sector, and so we'll be able to make direct comparisons of in situ measurements by the Van Allen probes in the equatorial plane with the precipitation seen by Beryl. This is, we don't have time for this, but this just shows you that the Van Allen probes over here are over in the wrong local time. But GOES was over in the right local time of the balloons, and these are the balloons I'll show you. And this is what Beryl precipitation data looks like. So the shock arrived here around midnight on January 17th, and then you see these spikes in relativistic electron precipitation. And they're not occurring in this case. There's some enhancement here associated with the shock, and here's some enhancement, and here's some. But the real spikes in precipitation are associated with substorm activity in the tail, it would seem, for this particular event. And so this is something that we are analyzing. Again, we are able to run test particles in the LFM fields for this time period, and I'll let Tiago give you a talk in October about an earlier campaign. But this is the MHD simulation for this time period. It shows the inward motion of the magnetopause. It shows the ULF wave power, which is not as high as it was for the October CME shock. And it shows the, again, loss of test particles to the magnetopause. What Tiago will come back and tell you about in October, because I think he's already signed up for a colloquium, is that he has been able, for an earlier storm event, and he's working on this one, to simulate the ULF wave modulated precipitation. So this just shows you for this earlier event that, and for others that have been seen by balloons, that you see ULF wave modulated precipitation of the electrons, and so he'll tell you about what the mechanism is that enables the ULF waves to change the electron mirror altitudes such that they wind up striking the atmosphere. Okay, so I think I'm out of time. Another talk, another day. There's a whole nother story associated with the proton measurements on Van Allen probes. I got this figure from Dan Baker just today on the telecon. And this is the energy ranges up to a GeV and proton energies, and down to plasmasphere energies by the HOPE instrument, which is the third component of ECT. And so, concluding, the highly variable MEV trapped electron flux is certainly strongly affected by CME shocks at solar maximum, and the launch of the Van Allen probes was, was driven to have them up there for solar maximum and the declining phase. And we are working on comparisons between atmospheric and radial losses, and we are using some other spacecraft. Certainly we will always look at GOES, and we're looking at Themis. The January 17th event is particularly nice because Themis was coming through the magnetopause, and so these are three spacecraft coming in a train, a string of pearls coming right on through as the magnetopause is moving earthward. So that's a particularly nice event to study. And we have colleagues that are providing ULF wave data. The CRRES chain in Canada is a regular participant with Van Allen probes to try to understand better what the relationship is between ULF waves and both the losses and acceleration of the electrons. And I think that's all I have time for. Okay, thank you. Yes. Yes, yeah. Yeah, it's great that you guys have that, because again, the Van Allen probes were over on the wrong side of the magnetosphere for this particular, and I think so it's going to be a very interesting campaign coming up in January when Van Allen probes will be over in the dust sector. Yeah. And hopefully yours will still be operating, yes? Yes.
I have a question about the set figure.
Yeah? Oh, the nugget. You know, let me tell you about that nugget. We tried to pass that up to headquarters as a nugget, and we were told, this is way too complicated for NASA administrators. So the kibosh was put on it as a nugget, but it's going into GRL. Yeah.
I saw figures of the pitch angle for the pitch angle for different events.
Yeah.
I think it's the 17th
of January. Yeah.
And the evolution of the pitch angle there shows which I think is expected, shows a C shape because
oh well, but maybe they were showing both. They were. This is maybe only showing one half of the pitch angle space. I think.
Right.
Yeah.
So it seems a bit odd to me that it's only one.
But because they're not showing all of them. Look, that's only. I think they've got it like 1,000 sectors or something. So they're not. They're only showing a half of the pitch angle space.
So it's not centered at 90 degrees.
No. I mean, they're not showing both halves. They may show 90, but they're not showing both halves.
So ask Seth for his version of the paper, because the figure in the paper has each runs the data there.
you can see the wave profile, and then he lines up very clearly the pulses in the wave with the actual pitch angle, and you can clearly see the
Yeah. Yeah. I actually already sent you that paper. It's okay. Yes.
So I got that paper also. Are the waves there seen also in the magnetic field data, or?
Yes, they are. Yes. So read that paper. It's great.
On the spacecraft and on the conjugated ground magnetic field.
Yes. Yeah. Yeah. Absolutely. Same frequency. Yeah. Okay. And interestingly, they're only observed at one of the CRRES stations, which means that they're very localized in, spatial extent, in radial extent. Yeah. Yeah.
Another question on another paper I haven't read, the one by CRRES.
Uh-huh.
Go to that one.
Okay, is that way? Yeah. No, it's this way. There. Yeah. Okay.
So after that peak forms, you continue to have growth in the phase space.
Yeah.
What is going on there? Why is that?
Well, so first of all, I think that you're continuing to have this enhanced radial transport, and then Brian CRRES would say the magnetosphere is relaxing during that later time. The ring current is subsiding, and so you have an increase in flux due to the inverse DST effect. You're conserving the flux inside a drift orbit, and so the electrons are moving inward as the magnetic field relaxes, and that increases the flux. So he thinks there's a significant amount of adiabatic effect, but in addition, you're continuing to have ULF waves during this time period that are going to smooth out the gradient, but you're obviously continuing to accelerate electrons. I mean, Richard Thorne has a paper that he was going to submit to Nature this week, so now he's not going to submit it until after the Van Allen probe meeting next week, that he is going to talk about the time scale for the local acceleration, and claims that it's fast enough to give you the thing that just knocks my socks off is this jump right here, right? I mean, once you get up to that, then I can imagine normal radial transport processes will continue to amplify things at the later times. Yeah. Mm-hmm. But there'll be more, because I think it's just great to be able to pin it down with the two satellite measurements, because there's always this question: was it a temporal change, et cetera? Yeah. Others?
So the first jump is associated with subspace activity.
Here, not here. This is during a period of time when, it is in the sense that you have this like 12 hours or more of very strongly southward IMFBZ that's driving substorms continuously, that are bringing the seed population in continuously. And when the seed population of electrons drifts around to the dawn side, as it's moving into stronger B, it has a strong temperature anisotropy, T perp over T parallel. It excites the whistlers, then the whistlers heat the electrons, and you're just continuing to drive that during this time.
One comment on this figure is very high at a more like 4 or 5.
Yeah, it's true. And that's why Brian would argue that wherever his figure is, there it is. That's why he would argue that you have to have this enhanced source population to radial transport in order for that to be effective. Yeah. Mm-hmm.
One more thing. So Janet hasn't spoken up, but I'm going to speak anyway.
Yes.
She's done some marvelous work with pose data, and during these, from that low altitude measurements,
yes,
there are incredible measurements from multiple satellites of pose.
Yeah, and I think, for example, Robin's communicating with you about the barrel times, right? Yeah, right. Yes, yeah, absolutely. Good. Yeah. Okay. Right.
Thank you very much.
Mm-hmm.